Okay, on to the second day of 3-6, which is the last day of notes for this class, for Unit 3, not the class in general, right? Just Unit 3. So on this one, what have we studied that helps us to sketch graphs? So if you guys look back at the other examples from day 1, we were analyzing tables and graphs of f and f prime and trying to come up with new stuff. Today we're going to focus on if I give you a function, can you graph it using all these tools? Well, let's just make a list. Again, if you want to try these on your own, go ahead. But what have we studied so far? Think back, Algebra 1. Did you guys learn x-intercepts? And if you know x-intercepts, can't you find y-intercepts? So these are good points to have on our graph. Now, kicking it up a notch this year, now we learned about critical numbers. When the derivative is 0 or does not exist. This helps us to possibly find some relative max and mins. We can also tell now if a function is increasing. We didn't know how to do this before because we didn't know that it's when the derivative was positive. We also can find when a function is decreasing, and that's when the derivative is negative. Now, if we're testing increasing and decreasing, first derivative test helps us to find relative max and min. The relative max we'll look at first. Do you guys remember what that is? That's when f prime goes from positive to negative. If I'm looking at relative max, why don't we also look at relative min? Relative min, think about we go down to go up. That's when f prime goes from negative to positive. After we were done testing first derivative, we went on and said, let's look at the second derivative and let's look at concave up. What's concave up? Two reasons I am hoping you're thinking. It's when the second derivative is 0, but it's also when f prime is increasing. I want you to think of those guys always together. Also, we have concave down. That's when the second derivative is negative or f prime is decreasing. You know, if we're testing those, then we better find inflection points where we change concavity. So inflection points, there's two ways. F double prime changes, that's delta, that's a symbol for change. So F double prime changes sign, or f prime can go from increasing to decreasing, or f prime goes from decreasing to increasing. Do you guys remember back from 3-5, we threw it in Unit 1? Horizontal asymptotes help a lot. What do horizontal asymptotes do? Or how do we find them? Do you guys remember it's the limit as x goes to plus or minus infinity of f of x? We could also find vertical asymptotes. That's when the point doesn't exist or the value doesn't exist. And there's a lot, right? We could keep going on. I'm thinking you could test even or odd behavior. That's the other one I'm thinking of. We could add that if you want. Okay, so look at 6. This is just asking us, saying we know the derivative is negative for all numbers on 2, 8. What does this mean? If this is 2 and this is 8, now here we go with this translation. They're giving me data about f prime, but they're asking me about f. So if f prime is negative, that means f is decreasing. I don't know what f is doing, but I start up here and I go this way. I could go this way. It could be linear, right? It could kind of do this. But all I know is that from 2 to 8, f is decreasing. Why does f of 3 have to be bigger than f of 5? Well, looking at this, if f is decreasing, doesn't that mean any value after f of 2 will be less than f of 2? So couldn't I say right here, because f prime is less than 0, that means f of t is decreasing. So if we know that the value of the function as we move left to right is decreasing, then anything after this 3 has to be less than 3, right? If f of 3 is here, it has to be greater than anything to the right of it. Okay, and we knew all this because f prime is negative, f is decreasing. Okay, now here's a problem that you're going to see on day 2. It's asking you to graph this. Remember, always I want you to notice domain restrictions first. So this domain goes from negative infinity to 0 and 0 to infinity, right? We can't have a 0 in the denominator. So we're going to go through and graph this using our calculus knowledge. Please do not use your calculator. So the first thing we're going to do is find the derivative. But before we do that, how about we make this calculus friendly? So the derivative is going to be x to the negative 2, which is 1 over x squared. Remember up above in our list, if we set the derivative equal to 0, it does not exist. We get critical numbers, then we can analyze relative max and min and all that stuff. So let's go ahead and do that. So our critical numbers are going to be when the derivative is 0 or the derivative does not exist. When does this happen? This happens at x equals 0. So x equals 0 is a critical number, and this is what we're going to test. Now, is it a critical number though? Look back up above. Didn't we say that the domain can include 0? Okay, so this is going to be a domain restriction, not necessarily a critical number. Okay, but remember in your chart, you still have to check domain restrictions, your discontinuities. So our interval, and then we're going to test the sign of y prime, and then we're going to say, well, how does that affect y? So we're going to go from negative infinity to 0 and 0 to infinity. If you look right here, look at the derivative. We're going to be quick about this. Without even subbing numbers in, isn't this always guaranteed to be positive because it's squared? So we know the derivative is always positive, which means to us, y is always increasing. Okay, y is always going to be increasing. So what does that mean? Doesn't that mean no relative max or min? Because the sign of f prime does not change. The sign of y prime does not change. Okay, so we have a function that's always increasing. That's what we know so far. We also have a discontinuity at 0. Okay, going on. What would you guys do next? How about second derivative? We're already on a derivative kick. Let's go ahead and do the second one. Okay, so the second derivative. Look up above. Here's your first derivative. I like this form better than this form, right? Because this is already calculus friendly. So we're going to get negative 2x to the negative 3, which is negative 2 over x cubed. Now to find our pips, it's going to be where the second derivative does not exist or when the second derivative is 0. Well, look at your second derivative. This can never be 0 because the numerator can't be 0. But it can not exist when x is 0. But what do we remember about 0 to begin with? It never existed in the problem. Okay, so that's a pip, a potential one. It's never going to be an if, an actual one, because 0 never existed. But the function could change concavity, so we still have to test it. So we're going to do interval sign of y double prime and the conclusion of y. We're going from negative infinity to 0 and 0 to infinity yet again. Let's see what happens here. We don't have something raised to an even power, so we're going to have to analyze this. If I throw a negative in, I'm going to get a negative times a negative, which is a positive. If I throw a positive in, I'm going to get a negative. Again, a positive into this value times a negative. So what does that mean if the second derivative is positive? Remember, positive, happy, up like a cup. If the second derivative is negative, we are down like a frown. So look at, we do have a point of inflection because the concavity changes. So we're going to have y is concave up from negative infinity to 0, and y is concave down from 0 to infinity. But let's back up. Is there a point of inflection? We want there to be one at 0, but remember 0 never existed. So even though we change concavity, there's not necessarily a point of inflection. Looking up above, what else could we determine? Look here. Can't we say by looking at this that x can't be 0? It doesn't factor away. It's non-removable. So we know that we have a vertical asymptote. It's another observation we can make. We have a vertical asymptote at x equals 0. What else did we analyze? Horizontal asymptotes. Isn't that when the limit, remember guys from your from an old test or quiz, when they say horizontal asymptote, you have to know that that means when x goes to infinity or when x goes to negative infinity. You have to test both. In both cases though, look, as x gets huge, 1 over a huge number is gone. X gets huge, either in the positive or negative, that's gone. So in both cases, we get a 1. So we have a horizontal asymptote at 1. We skipped over the easy stuff, which are the asymptote, which are the intercepts. Look right here. X can't be 0, so we can't have that intercept, but couldn't we let y be 0? Let's see what happens there. If y is 0, aren't we going to have 1 equals 1 over x? So x is 1. So we have this as our intercept. Okay, let's see what we can do with this. Let's go ahead and plot our intercept at 1, 0. What else do we have, guys? We have some asymptotes, I recall. We have a vertical one at 0, and we have a horizontal one at 1. Okay, we have a point on the right piece, so let's deal with this first. What's going on from 0 to infinity? We have y increasing, and we have y concave down. So it's not going to be the whole bowl. If I'm increasing and concave down, it's going to look like that. And do you guys see how that lines up with our asymptotes? Okay, let's see what's going on the left. So from negative infinity to 0, I am increasing and concave up. Now that seems to match up in here. I like plugging a point in just to see like some point of reference. Let's make it easy and let's sub a -1 in. If I sub a -1 in here, 1 over -1 is a -1. 1 minus a -1 is 2. So at -1, I get 2. And recapping what I just said, we need to be increasing and concave up. So this is going to be increasing and concave up. Everything matched up. This with our asymptotes, this looks beautiful. Okay, so when they ask you to graph using calculus, that's what they're talking about. Okay, next one is a little refresher. A slant asymptote. I hope you guys remember this from pre-calc. If not, I'm going to go over it. So you'll have a slant asymptote when the degree of the numerator in the top exceeds the denominator by 1. So let's look at this. The degree in the numerator is 2. That's a 1, 3, and that's a 2. This is how you'll know you'll have a slant asymptote. To find it, we're going to do your favorite thing and do long division. So we're going to say x plus 1 goes into 3x squared plus 4x minus 10. To do long division, you say how many times does x go into 3x squared? And that's a 3x. You then multiply these two things, and you're going to get 3x squared plus 3x. You then subtract, and you get x. You bring down the 10. Now the question is, how many times does x go into x? And we would say once. You then multiply 1 by x plus 1, and you get x plus 1. You subtract again. Hey, a common mistake in here is you forget to distribute this negative. Okay, so then we're going to get, actually we're doing too much work, because once we get to this part where we know that those are going to cancel out, this is our slant asymptote. So we really didn't care about our remainder. So your answer is 3x plus 1. This will be your slant asymptote. Okay, try the next one on your own. On this one, you want to watch out for placeholders. So there's a 0 there. Also, it goes x cubed plus 0x squared plus 0x minus 4. This is going to take a couple rounds. How many times does x squared go into x cubed? That's an x. Notice that I like keeping this nice and neat. All my x's are lined up, constants and squareds. I chose to write this x here because that's where the x is. Now I'm going to multiply x by x squared plus 2x. And I'm going to get x cubed plus 2x squared plus 0x, and then I'm going to subtract. The x cubes are gone. That was my whole point. Then I have a negative 2x squared plus 0x, and I bring the 4 down. But I think that was a negative 4, so let's fix that. Now the question, how many times does x squared go into negative 2x squared? How about a negative 2? Do you get now we're done with our slant asymptote? Like we're at the end of the fraction bar. We don't care about the remainder. I'll go ahead and finish it up, but know that you probably really don't care, especially if you're tight on time. And then we have to subtract all that. Make sure we wrote that right. Looks beautiful. Okay, these cancel. This is a negative, positive, so we have a 4x. And then I'm going to have a minus 2. Okay, so looking at this, the slant asymptote is x minus 2. It's this answer right here. Okay, on to 9. Oh, this is it. Guys, end of the chapter. Okay. Oh, just kidding. There's 3, 7. Totally forgot about that one. Sorry. Okay, explain why there is no vertical asymptote, even though it appears that there should be one. Doesn't it seem x can't be 1 vertical asymptote? Oh, but we know better because we are chapter 1 experts. Doesn't the top factor? Oh, look at this. What happens? That cancels. That's removable. That's why we don't have a vertical asymptote. So we can say there is a, what's it called if it canceled? We removed it. There is a removable discontinuity at x equals 1. Also, do you guys remember the definition? If we take the limit as x approaches 1, and I'm going to write the factored form. Remember, if this is the graph, and I'm making this up, as you approach it, to have a vertical asymptote, you either have to go to infinity or negative infinity. That's how you know you have a vertical asymptote. So if we were to take the limit as we approach this, do you guys see these cancel? And now you can do direct sub, and you get a 3. So in order to have a vertical asymptote, what did we want? Didn't we want the limit as x approached 1 of g of x to either be plus or minus infinity? And instead, we got this lovely 3. Okay, I mean, this was the quick way to say it canceled out, it's removable, it's not a vertical asymptote. This is the definition. And I just want to keep reminding you of that. Vertical asymptote is when you take the limit and you get either plus or minus infinity. Okay, kiddos, done with 3-6. We're out.